Let us solve a problem using Picard's method. We are given with a differential equation dy by dx equals x minus y with the conditions y equals 1 and x equals 0. We have to find out y for x equals 0.2 correct up to 5 decimal places. We are asked to check the solution by comparing with the exact particular solution. We are also asked to find out 5 approximations of y. We have initial values x naught equals 0 and y naught equals 1. Also f of xy equals x minus y. When you have dy by dx equals f of xy and you take integral dy equals integral f of xy into dx, you arrive at the formula y equals y naught plus integral x naught to x f of xy into dx. We have f of xy equals x minus y, x naught equals 0 and y naught equals 1. Thus we get this equation. Here in this equation, when you give y equals y naught, you will get first approximation. That is, first approximation y1 equals 1 plus integral 0 to x minus 1 into dx. In this equation, when you give y equals y1, you will get the second approximation. That is, second approximation y2 equals 1 plus integral 0 to x minus y1 into dx. Third approximation will be y3 equals 1 plus integral 0 to x minus y2 into dx. Fourth approximation will be y4 equals 1 plus integral 0 to x minus y3 into dx and so on. We have first approximation y1 equals 1 plus integral 0 to x minus y0 into dx, where y0 equals 1. Thus, after usual integration, we get this function as the answer for first approximation. We have second approximation y2 equals 1 plus integral 0 to x minus y1 into dx. We have x minus y1 becomes x minus 1 plus x minus x square by 2, giving y1 equals 1 minus x plus x square by 2. Thus, we have y2 equals 1 plus integral 0 to x minus 1 plus x minus x square by 2 into dx. After usual integration, we get second approximation equals 1 minus x plus x square by 1 minus x cube by 6. That is, y2 equals 1 minus x plus x square minus x cube by 6. We have second approximation y2 will help us to find out third approximation y3. We have y3 equals 1 plus integral 0 to x minus y2 into dx, where y2 is this function. After usual integration, we get y3 equals this function. This expression will help us to find out y4. We have y4 equals 1 plus integral 0 to x minus y3. When we do the usual integration, we get y4 equals this function. Similarly, we have the fifth approximation obtained as y5 equals 1 plus integral 0 to x minus y4. After usual integration, y5 is obtained as this function. When you give x equals 0.2 in all these approximation, we get the particular values of each approximations at the particular point x equals 0.2. Notice that fourth approximation and fifth approximation values at x equals 0.2 are exactly the same, considering 5 decimal places. Now let us verify the solution. We have dy by dx equals x minus y can be rewritten as dy by dx plus y equals x, which is of the form dy by dx plus p into y equals q of x. For this kind of differential equation, we will find out the integration factor e raised to integral p dx, and we have the general solution written as integral q into integration factor plus c equals y into e raised to integral p dx, where y is the dependent variable which occurs along with the function p. In this given equation, we have p equals 1. P into y equals 1 into y. Hence, we have function p equals 1. Integration factor e raised to integral p dx equals e raised to integral 1 dx, which is e raised to x. We have q of x, which is a function on x equals x, which occurs in the RHS of the equation. Thus, we have the general solution written as y into e raised to x equals integral x into e raised to x dx plus c. We can integrate integral x e raised to x dx using integration by parts, considering x as the first function and e raised to x as the second function. Thus, we obtained y into e raised to x equals x minus 1 into e raised to x plus c. When you multiply both sides of the equation using e raised to minus x, we have y equals x minus 1 plus c times e raised to minus x, because e raised to x into e raised to minus x equals 1. Since e raised to x minus x equals e raised to 0 equals 1. Thus we arrive at this general solution for y. In this equation, when you give y equals 1 and x equals 0, we will get value for c as c equals 2, which is the particular solution. In this particular solution, which is given by equation 2, when you give x equals 0.2, you will get y equals 0.83746, which is exactly the value which we have obtained in Picard's method as the fifth approximation of y. We have verified the solution of Picard's method using exact particular solution.